Hi and welcome to exercise 6 of structural analysis with Robo. So on exercise 6, we want to model this beautiful truss, okay? And the goal here, as you can read, is determine the reactions at the truss supports A and B, right here and right here, okay? The distributed loading is caused by wind. So it's as if this truss is what sustains the roof structure of a particular building. But well, how do we model this in Robo? Okay, so let's just go straight and do that. Okay, so before we get started, I would like to indicate that Robo does have a particular module which specializes on 2D trusses. Okay, so if you come right here to new, okay, you have the possibility of choosing this truss 2D design, okay, which is specialized for trusses. Maybe let's just go right ahead and use that. Not much changes, right? Because the principles all through robot structural analysis professional are basically the same. Okay, so even if I modeled it on the 2D frame, it won't change anything much. Okay, so I want to show you guys a quick way, a rapid way of modeling that truss, okay? And in other trusses, we will be using the conventional manner. But in this particular truss, I want to go really fast about it. Robot does have a database of typically used structures, so structures that people are more prone to model, okay, because of their repetitiveness in real life, in daily modeling. Okay, so if you come right here to library of structures, you will see a list of such typical structures. Okay, so here, for example, you have a continuous beam. Here you have frames. Okay, you have other types of frames. Grid here and different types of trusses, as you can see. Okay, so the database continues down. Okay, you even have shells and plates that you can model rapidly. Okay, just change the geometries and you have what you expect. So what we want to do here is to look at these different trusses here and see which one is similar to what we want to model. Okay, so obviously if you have a truss that is not found here, it does not mean that you cannot model a truss in Robo, right? You just have to draw it element by element and flow along. Good. At this level, want to identify where is this truss here, okay? And we can see that this truss is much similar to this one here, right? If you look at the inclination of the bars, this, and that, okay? Oh yes, these trusses have specific names, by the way. So we'll just select this one and then we'll go to OK. Now, all we need to do is to enter the different parameters, okay, in such a way that it corresponds to the trust that we have. Now, we will be entering these things detailedly as we go along, as we see more trust examples, and as we enter into trust design when it comes to steel design proper, okay. So for now, we just want to model that as fast as we can and very, very briefly. Okay, so I will just explain the useful parameters here. Okay, first diagonal up, we'll look at that. We have the length L here, which is the overall length of the truss. We do not start by choosing a unit here because we know that by default it is the imperial unit, right, that our robot opens with. This particular one I'm having here, okay, yours may be metric according to the parameters that you've set. Okay, so here the length L, that which is the overall length as the diagram shows, we can see clearly here that the length L is 48 plus 48, which gives me 96. Okay, so I will have 96 for the length, and then for the height H here, I will have 20 feet, right? So we want 96 here, and here we want 20, right? Uh, what about the number of fields? Number of fields speaks of the spaces that are delimited by the various what's that? By the various peaks. Okay, so you have these, these, these straight bars here, right? That's what delimits the field. So from point A to that will be one field. Here to here will be one field. Here to here another field. Here to here another field. Okay, so that's what we understand by field in trusses. So how many fields do we have? Here we have 1, 2, 3, 4, 5, 6. Okay, so you can see fields as internal spans, right? So 6, we have 6, just like here 6. Okay, so we are good to go. So continuous chord here speaks of the way robot will finally represent your truss. Okay, so these are the chords here, right? These are the chords right here. So will Robo represent it as a continuous beam, just one beam, okay, to which all of these others are connected, or do you want Robo to represent it discontinuous? So this one is an element, this one is an element, this one is an element, this other one is an element, this other one. So for now, we'll just take it continuous, okay? No big deal. And the moments released, of course, yes, okay, moments released at the level of the nodes, okay, to be sure that we are not transferring moment from one node to the other. It is just axial loads, right? Good. Um, it's just forces, not rotations. We don't transfer rotations, we transfer just forces. Good. That's better. Okay, so if we're finished with that, all we need to do, you see, there are other options here like sections and all the like, but we don't really need that for now. Okay, we don't really need that for now because irrespective of the section, our reaction will be okay. Our reactions won't be affected. So we'll click on OK, and this is our truss right here, or a beginning of it, right? But we will see that our truss don't have these other diagonals here, this one and this one, right? So we can just click here. Okay, I'll select those bars. Okay, you press one, you control to select the other one. Okay, so two of them are selected, and we can just press delete. Okay, on our keyboard, and that should do. I think now we have our exact truss, right? We have our exact truss. So automatically when you choose 6 fields, it will be 6 fields that are equally spaced together. Okay, so normally the middle from here to here will be 48. Okay, you can see it even from 0, it stops around 48. Okay, and then right, it stops right up to 96 somewhere. Okay, good. So what's the next thing we want to do? The next thing we want to do is to put the support, right? We have a pin support this way and we have a roller support this way. So let's go ahead and add that. We'll just click right here, and the roller support, we said it is on this node, so we'll click on that, node 7, and then the pin support is on this other node. We'll click on that, node 1. Okay, I hope that's a pin support. Why is it modeled as a fixed support? Let's look at its definition very well. Okay, UX use it. Sure. Okay, just to be sure, because okay, so that's a pin support. Let's be sure about the difference here. We have UX user, the same thing. Okay, so what I will do is just to be on the safe side, okay, we will remove that support. I'll just press Control Z here so that that support is eliminated, and let's define a pin support, and we'll call it 2. Okay. Oh, perfect. It's not a problem. So let me explain that. Oh, that's interesting. Okay, let me explain that. When it comes to trusses, right? The pin is modeled as a fixed support because it is assumed that trusses have only 2 degrees of freedom. Okay, only 2 degrees of freedom. So you will not see rotation around around M there because they are not expected to resist forces via rotation, okay, to resist stuff like bending moment and stuff like that. So it is only forces that they resist. So to say you are blocking all directions in trusses, remember we are in the truss model, right? To say you're blocking all directions in trusses would be similar to saying that you're blocking UX and UI, because those are the only degrees of freedom that a truss has. Okay, translation, no rotation. That's the way it transfers its forces. Good. So that was great. So now the next thing we want to do is to apply the loads, right? So to apply the loads, we'll just add the load definition here. And let's not do the mistake that we did in the previous exercise to forget that we need to delete the self weight. So to do that, I'll just go to load tables, and so remember, this self weight is very important when it comes to design. Okay, it's because we are doing simple structural analysis for now that we delete it all the time. Okay, so that's taken out of the way, and now we want to define the loads. Okay, so what loads are we having here? We have uniformly distributed loads, right? As you can see, they are perpendicular to the inclination of the bars. And what best is there to do this? Good. We have another problem here. Okay, so for this modeling, we will not be able to use the truss module, okay, because the truss module expects forces to be at the level of the nuts, okay. The modeling of trusses expects forces to be at the level of the nuts. Okay, so what we can do here, we don't have to restart the whole thing. It's interesting. It's interesting. We don't have to restart the whole thing. We can simply change the module, okay, that we are using. So for that, we will come to geometry, okay, and under geometry, we will just choose structure type, and we can go back to our 2D frame. Okay, yes. So let's save that as our exercise 6 and save. So that should take us back to the 2D frame module where we have better loading options and other stuff. So you already see that the transformation has been done here for the pin support, right? It has become a triangle back. Okay, it is no longer like the same as a fixed support. Great. Okay, so we can then go and model our loads in bar. So you see that all these options now are activated. So this should give you the difference between using different modules. Okay, you have some options that are activated for specific structures, which are not activated in others. Okay, so we want the uniformly distributed load, right? And here obviously we will choose what the local coordinate system. Okay, you remember why from the previous exercise, right? Because the local coordinate system, this is it right here, we want the load to be perpendicular to the inclination of the bar. Okay, so we want the load in this z direction, this local z direction, not in this global z direction. Okay, so how is that load? It is downward, so it is opposite to that inclination, right? We'll have it to be here. It is in keep per feet. So what we want to do here now is to go and change the unit of the force, right? So that it should be pounds. So let's close this first. Okay, and we'll go to tools and job preferences. Under job preferences, we'll go to units and add at the level of forces. We don't want kips, okay, we want pounds, right? And obviously, just for uniformity, let's just change everywhere. Okay, uh yeah, yeah, this can still be per feet. Okay, so we'll change that. The stresses, we're not into stresses right now, so let's go. Great, so we can go back again and define our forces. Okay, at this level we will have negative 600, right? Local coordinate system, negative 600 local coordinate system, right? And we can add that, and then we will select this bar, right? So you see that we can select this like that because it is what? It is continuous curved. Good. So let's put the labeling there. So that is 600, negative 600 pounds, right? And then for the order, it is in the direction of the local coordinate system, right? And it is 400 pounds per feet. So let's look at that. So that's the direction. Okay, it is upwards. So it is 400 pounds, just positive in the same direction. Okay, local coordinate system, we add that and we can come and apply it right here. Okay, so that's it, upwards. Good. We can close, and that's our modeling. That's our modeling, right? So what is left to do here is just to calculate and then check the reactions, right? So let's go ahead and do that. I calculate. Okay, so still instability. We'll look at what that means in future videos. Okay, so we can close this. Let me remove the forces and remove the coordinate systems. I just want to see the results at the level of the reactions. Okay, let's just activate Fx and Fy. That's what we want to see, right, with the descriptions. We'll apply that and close. So let's check these results. We'll have to go back here. Okay, so answers, that was 2.26, right? So 2.26, we have 5.12 5.12 kilonewton. You see that here there is a mistake in the level of the book, right? They've written 5.12 kilonewton, whereas those forces are not in kilonewtons, they are in pounds. So this is a major mistake. But the fact that I've put kilo tells us that it is in thousand, right? It's supposed to be 120 something. Okay, so that's what we have here. Okay, this is what we have right here. Let me just go down to the answer here. Okay, to 26. Okay, that's what we have right there. If you estimate it to two decimal places, the 6 will come up here to, for us to have 5.12, right? So that's what we have right here. And then we have here kilo, so it is 14,700. So this is a mistake from the book. Okay, we have here 14,716. Okay, so that's correct. That's for AY, so which is FZ exactly. And then we have 20,000, right? And 20,000 here. Okay, so that's correct. I hope this was useful. Yeah, that was very enriching. We played with model, like, and that's great. So see you in the next tutorial for the next exercise. Bye bye.